In this demo, we'll be using R to explore and analyze a dataset using the Iris dataset. So a little bit about the Iris dataset. So it consists of 150 samples of the iris flowers, and each of these belongs to one of these three species. We have Setosa, versicolor, and virginica. And these are the other attributes, right? So, and all of them are numerical variables, meaning they are continuous. Now, each sample in this dataset has four attributes, namely the sepal length, sepal width, petal length, and petal width. Okay. Now, they all measured using centimeters. Now, the sepal is just a part of the flower that protects the petals, the bud stage, right? While the petal is just a colorful part of the flower that attracts pollinators, right? So these are very popular data set that comes from the UCI archives or repository. We're going to import that from there. So essentially, this is just a nice data set if you're interested in machine learning, data analysis, or data visualization. This is just a gold standard for that. So the first thing we want to do here is to import the packages or install what packages we're going to be using in this demo, right? So just wrote this code to just automate this process. So let's look at this code over here. Now, so this code here just defines the vector, right? We give this vector the name package names, abbreviated as that, right? These packages are listed using the C function here. We concatenate, right? So we need to, just include dplyr all the way to here. Again, so we're just creating a vector of packages, right? The next line of code here. So what this does is that it just checks for these packages. Are they already installed on the system? If not, then it will install that and it will compare with what we already have here, right? So again, this part of the code here, again, this part of the code kind of just checks and returns a list of installed packages. In fact, let me just copy this and put it at the console here. So you can see here, it returns all the packages that are installed in my system, right? So again, this part of the code here just checks, right? These packages here, are they installed? Do they exist in this list of packages that are installed on the machine, right? Okay. And then that expression now just returns a logical vector that indicates which package are not installed, right? And then we store it under here, right? So this is what it does. So this is done by creating a new vector, the missing packages, right? This only contains the missing packages, right? Again, then just checking for its length. Okay. So, and here again, we're just checking for the length. So if it's not 0, meaning that it's not empty, then that package is missing, right? So it kind of just, after the curly brackets, going to install that package, right? So, and install that. Again, this missing package, it just checks for the length. If it's not empty, okay, meaning that it's not 0, it's greater than 0, then those packages are missing. So we better install that. So all in all, this code here just sort of just checks for the presence of the specific package and installs them if necessary. Okay, this just ensures that the required packages are available for subsequent analysis. You can always add as much as you can using the comma to concatenate them. All right, once we have that, we load all these packages that we've already installed. Okay, once we do that, the first step is to load the dataset and explore the variables. So in this case, we're just gonna load this dataset. So this code, what it does here, we're gonna use that. So the data here will be read using the CSV file, okay? And it comes from this URL. In fact, if you go to this UCI repository, this is where the data can be downloaded, but we already have the URL here. If you copy this on your browser, it will automatically download this data set. Okay, so the header here equals to false just this argument specifies that the files does not have column names, right? So instead, we need to provide our own column names using this call.names, right? And then we concatenate and provide the vector here, right? So this would be all our column names. And then the class here is where we specify the last column represent the species of the flowers, okay? So I've already run this, so I'm just gonna keep explaining the code. Again, here, Glimpse just provides a concise summary of the structure of our data frame. And you can see here, each of this attribute is provided and the class here, okay, some sample data set. The summary here just gives a summary, some statistical summary of our data set, right? As you can see here, the minimum length for sepal length is 4.3 centimeters. The maximum is 7.9 centimeters, right? And the mean average here, or that rather the mean or the average for this column or attributes is 5.43. Okay. Now let's move on to the next step. So the next step here, we want to preprocess. So preprocessing is a very important step in machine learning, right? Now this code just performs some data preprocessing on the Iris dataset. Again, we use this pipe operator. This pipe operator comes from Magritter package, okay, which actually comes from Tidyverse, but we can import that separately, right? So this just allows us to chain together multiple functions, right? So in this case, our data set is called Iris data. In fact, here, once we imported our data set here, we stored in this box or variable or object called Iris data, right? So our data frame or data set now here, so we want to chain this. So this data set is being passed through different functions. And the first function is select function here, where we are saying we want to select all the columns, right, in our data set except the class column. So that's why we use this negative sign in. We want to exclude the class column, okay? So that's what it means. And then this is actually right. Then, right, we scale. So this scale function, actually comes from the inbuilt R function. So it's just centering and scaling the data, okay? What this means is that we just want to subtract the mean of each column. So if you come here, you see the mean of this. So for example, this sepal length, we want to subtract the mean of this column, which is 4.3, right? So this is subtracted for every value in that column. So if we go to sepal length here, so you can imagine each of these values separated from the mean, right? So once we have that, then the result is divided by standard deviation of that column. I just did some standard deviation for sepal length. So we just use this function SD. Then from our data set, we want to access this attribute column sepal underscore length. You can see that standard deviation is 0.82. So you get all that divided by the standard deviation, right? So that's exactly what we are doing here. So this process just makes all the columns have, the goal for this is just to have the same scale, okay, which is very important for some machine learning algorithms, okay? And then the resulting, all these results is stored into this object, right, called Iris data norm, right, which is just a copy of all this data set, but with one less column that we already excluded here, all right? And the remaining columns are also centered and scaled. So this is what this code does. So our first clustering algorithm is called the k-means, right? So the k-means is a very popular algorithm. So let's look at what each of these does. So the first thing here is to, so this code actually just performs k-mean clustering on normalized data set. Remember, we've already centered and scaled this, right? So we use these k-means, right? So, but let me just start from here. So the set.seed here, 123, just sets the random seed to 123, ensuring that the results are reproducible. And then the k-means here performs the k-mean clustering on the normalized data set, right? And then this data set has 3 clusters. So we use centers here to specify, right? 5 actually. And then we are saying, so the random, we were saying 25 random starting points. So we use this parameter nstart. We just say this is going to be 25 random starting points, right? And then the resulting, actually here, the resulting object, right, is called the km.res. So we just give it some name, right, which contains information about the clustering, right? This will contain the clustering assignment and the coordinates of the clustering centroids, okay? The next function here is called fviz cluster. We use this to visualize the clustering results, right? Now, this function takes the following arguments. So again, we pass, our k-means clustering object, right, from our original data set, and then we specify where it's coming from. Again, it's coming from this data. And then we type the, and then the type of the visualization, we're going to be using ggplot. So that's why we actually just imported ggplot here, because we want to pass some visualization objects here. So here we're telling R that we want to use the point, right? And then the convex here is just the ellipse type, right? We can change this to something else if we want, right? Again, this is very important. Then the GG theme here, we just specify the type of theme that we want here. So for example, if I change this to dark, right? I could just change this to dark, right? And when I run this, you can see the theme here is just going to be dark, right? And then, of course, we have other, we could say convex here. In fact, if I come here and just type fviz cluster, right? The help function, very important. So we can see here the ellipse parameter here, the ellipse argument. Where is that? Ellipse type can be Euclid or norm or convex. So if we do Euclid and run that again, it just represents a different shape. Okay. And then here we just add the plus sign here, and this plus sign here will help us to add another geom object, GG title, right? And then we call, just provides a title to our plot. Okay. So overall, this code just performs k-means clustering on the Iris dataset. We visualize the results and allows us to do some further analysis and interpretation of the clusters. Now, again, so how do we determine the optimal number of clusters for k-means or for whatever algorithm we are using, but mostly for k-means, right? So to do this, we use this function, fviz nbclust, right? This is a function that comes from, so this comes from this package here, factor extra. So again, let's just go back here. And it takes the following parameters. So it's a very, the factor extra package is used for visualizing the results of different clustering algorithms, right? In our case here, we want to visualize this, what we call the within sum of squares, abbreviated as WSS, right? For a range of cluster values, right? Now, the first argument here is the data set, right? Remember the normalized data set that we already did in the previous step. And then the second argument is just the clustering method. We want to use k-means. And then the third argument is the method, right? This specifies what we want to use, that we want to use the WSS method to determine the optimal number of clusters, right? Now, this function, essentially, we just generate a plot, right? As you can see here. And this plot just shows the number of clusters on the x-axis, right, over here, and the WSS on the y-axis, okay? So the elbow of this plot is the point of the diminishing return. For those in business, you might have come across that, the laws of diminishing return. But anyway, so the elbow, right, is just the of the plot is the point of diminishing returns, right? Meaning that if we add more clusters, this might not lead to a significant improvement. So in this case, how do we choose the optimal number of clusters? So what number will be the optimal? So here at this point, we just want to select the one, especially where the elbow, where we have the elbow and then it starts diminishing. So in this case, we can already see it somewhere around here. So that's not surprising because from our data set, we know we have 3 species. So this would correspond to our 3 clusters. Okay. And then we can again come back here and feed back to our centers here, right? If we do that, again, we'll see that we generate some 3 clusters, and it kind of just shows us the misclassification here, right? So I'll change this to convex, for example, and I'll just change this to classic, right? Just to give us a different perspective, right? So again, that's just the limitation of using k-means. You have to, beforehand, you have to select the k value, okay? All right, so once we do that, we want to go to the second clustering algorithm. It's called DBSCAN. Again, the DBSCAN here stands for density-based spatial clustering of applications with noise. What it does here, the idea here is just groups together the data points based on their proximity to each other, right? Again, the clusters here are the dense regions of the data points, right? Represented by the regions of the lower point density. So again, here, what we want to do here is to preprocess the data and give it a different name. So just to, pass it to a new clustering algorithm, right? So the first argument here, the first function here, we're going to be using the DBSCAN, right? And then it takes the following argument. We pass our normalized data set, right? And then this EPS here just means epsilon, right? This just specifies the maximum radius of our neighborhood, right? For a point to be considered a core point. So in our case here, that would be 0.5. Then minimum points here, again here, just specify the minimum number of points in the neighborhood of our core point, yeah, to be identified, right? And then the resulting the resulting clustering is stored in this object called dbscan.res, right? Finally, we use the FVs cluster, and then we pass. Now here, again, the FVs cluster here just comes from the factor extra package, again, that we've already seen, used for visualization and clustering the result. Again, here it takes the following arguments. We've already seen that. We pass the results from the previous step. And then we use geom point, and then we use this classic, and we add a title, right? And then we'll end up having something similar to this. Okay. All right. And then lastly here, we have the hierarchical clustering, right? So for hierarchical clustering, we're going to be using the H-cluster, right? So this function is used, actually applies the Euclidean distance by default, right? On our normalized data set that we already normalized here and call it norm3, right? So this dist function here applies the Euclidean distance on our normalized data set, okay? Then the resulting object here is stored, the resulting clustering is stored in this object, right? And then the other function here is called cut tree. This function is applied on our clustering object. Then K here, we just tell R that we want to assign each observation to one of the 3 clusters, right? And then the resulting a vector is saved in this object called clusters H cluster, right? Then finally, we use this FVs dend. This function again comes from the factor extra package. Again, it's used to visualize the dendrogram. We pass our, so again here, we want to pass our resulting object, right? Which is just a hierarchical clustering object. And then this parameter here, this argument just sets the size of the labels on the dendrogram, right? As you can see here, the size of the labels on the dendrogram, right? And then 0.5 here, again here, actually it's just the size of the label, right? K equals to 3 here, just specify the number of clusters to display corresponding to the different species that we have. Then the K colors here just provides the color for each cluster, right? And then we just add another geom object here, just give the title, right? Now, another thing you can do here, we can click on this icon here, and you can see here, we'll be able to have a good representation of our data. We can blow it up. So this is the good thing about our as you can see here, this is actually a zoomed version of the same, right? All right, so now that we have that, so again, so the question is, how do we evaluate the clustering quality? We can use visualization here. As you can see here, we have quite a bit of misclassification. Even here, you can see we know that each cluster should have 50 data points equally, right? Again, here we can see, K-means does quite a bit of a better job here, but we have other evaluation metrics that we can use to determine the quality of a cluster. The one we're going to be using in this demo is called the silhouette score. Again, it's just a metric that we use to measure and compare different clusters, and the score ranges from -1 to 1, with a higher value indicating a better clustering result. So let's quickly look at each of this code here. Again, here we can see that for K-means silhouette, we have the following. So the first line here just kind of compute the silhouette score for K-means clustering algorithm, right? We apply that to a normalized data, right? Again, the silhouette function here just takes 2 arguments. The cluster labels, right? This is the cluster labels. How do we access that? We use this clustering object, $, to access the cluster, all right? The clustering labels. And the distance, right? And the distance matrix of the data, right? And this will be our normalized data. And then it will apply on the using a distance matrix, right? So again, so all these labels that are obtained from this object will be computed, right? Using K-means, right? Or rather, that was computed using our K-means function, right? And then once we have that, we get the mean of our result here using mean here. Again, here we want to select all the rows and the third column, right? In fact, if we just take this over here, so let me just take this to show you what happens here. So if I copy this over here and remove this 3, we can see we have 3 columns, right? And the first column here is the cluster, the neighbor, and then the silhouette width. So this is what we're interested in. So we're using subset here. We just want to extract all the rows, as you can see here, all the rows here, right? For only this third column, and then we get the mean. We just want to get the mean for this, right? So we use this cat function to do that. Then it will just give us just one value, right? We do the same for DBSCAN, and we do the same for H clustering as well. Just using what we already looked at before. So we just use the silhouette function here. Again, this will just compute the score for DBSCAN. We do the same thing. We extract the cluster labels, and then we get the distance from our normalized data set, right? And then that will be computed here, and then we store a result here. We get the mean as well. Okay. So once we have that, we can already see now the K-means, DBSCAN and Hierarchical, right? So again, from here, we can see a high score just indicates that the objects within a cluster are tightly packed together, right? Meaning they're well separated from other clusters, right? While a lower score indicates that the clustering solution may be suboptimal, right? In fact, if we go back here and change this to maybe 3, so if we do that, 3 here, let's see if that will improve. Then we go again and run here, see whether the scores will improve. Again, so the score actually for K-means has gone up, right? Once we pick the optimal value and put there as 3, we can see now the number has gone up, right? Lastly here, we can get a summary of DBSCAN, something I just wanted to talk a little bit about here. Again, here we can see the output here just shows the silhouette output, right, of 150 data points, okay, used to cluster DBSCAN with 3 clusters. Now, here the output just shows the cluster size. So from here, we can see the cluster sizes and ID. So we have cluster 0, 1, and 2. So for cluster 0, we have 34 data points. Cluster 1, we have 44 points, and cluster 2, we have 72 points, right? So again, here we can see for each of this cluster, right, the silhouette width ranges from -1 to 1, right? So in this case, we can see cluster 1 here has the highest silhouette width at 0.7188, right? Remember the goal, the higher the better, right? And then we can see cluster 0 has the lowest silhouette width. Okay, this might just suggest that these points may not be well clustered, right? So that's what it means. And we can see here, we can in fact, let me just run it again here. We should be able to see a corresponding mean. So this is 35. So you can see here, this is where the value was extracted from. So we have a mean for 0.35. Okay. All right. Again, we can see the minimum value is negative 0.75. The maximum value is 0.908. However, the mean for all these values we've already seen over here, in this case here, was 0.3578, right? Another thing I just wanted to mention briefly here. So with k-means clustering, we can also use other different methods. So for example, here, we can change this maybe to silhouette, right? Like that. So again, this will generate, so I think a spelling mistake here, silhouette. So there's an E here. So run that again. You can see it generates a different plot. So with the silhouette, right, you can see it's trying to tell us that the optimal number of clusters is 2. And, based on our data set, I think that's not right? Because we already have 3 species. So again, this is, you need to try different methods, right? And lastly here, we can even try something called gap stat. Again, it's a very popular method to evaluate, right? So as you can see, it just generates a plot. Okay, the higher the better. You can see ranges from 0 to -1 to 1. Again, at the top where I start tapering off, again, kind of just shows us that's almost 2 of them. So again, between 2 and 3. But in our case here, looks like WSS does a better job to show us the quality, the optimal number of clusters over here. Okay. So lastly here, in in conclusion, we can see that we've already demonstrated how to use the silhouette as a method to determine the clustering quality. So we have the elbow method. We've seen how to use the gap statistics. Additionally, you can use the DAN index, right? Adjusted RAND index and F measure, right? So again here, just to conclude what we have here. So the k-means clustering. So if we go back here, we can see that when using the k-means clustering over here, it's just a method that divides the data into predetermined number of clusters, right? With the clusters essentially having roughly equal variance, right? So again, one thing to keep in mind that this just works well when we with separated data, and the number of clusters is known in advance, right? In this case, you can see here, we used k-means of 5 centers, which was not appropriate. So having used the elbow method, we're able to determine that we need 3, right? And then the next type of clustering here, DBSCAN. Again here, this is just a density-based clustering method. The idea is just groups the data points closely packed together, right? This is a very good algorithm because it can detect clusters of arbitrary shapes, so which makes it more attractive. And again, it's not very sensitive to outliers, all right? But again, you just have to be cautious. It can be very sensitive to the choice of parameters that you use. These parameters include the epsilon and the minimum point. So again, you might need to use that sparingly. With hierarchical clustering again here, again, this is just a method that just builds on nested clusters, successfully merging them or splitting them based on some distance metric, right? Like Euclidean distance, right? Now, this method is useful when the number of clusters is not known in advance, right? And the good thing about the hierarchical cluster, it will produce for you a dendrogram, right? This dendrogram is very useful to visualize the clustering hierarchy, right? But again, just to keep in mind, the bigger the data set, it's going to be computationally intensive, okay? And for that reason, might not work very well on large data set. So in conclusion here, ultimately, the choice of your clustering method will depend on the nature of the data, right? And the problem at hand. So in this case, it's just useful to perform additional analysis like we've already done here. We've used Silhouette to evaluate the performance of the different clustering algorithms, right? And from there, we can determine which method is most appropriate. In our case here, just based on this, we can see that k-means here and hierarchical clusterings are most appropriate for our problem at hand. And that concludes our demo on, clustering in R using k-means, DBSCAN, and hierarchical clustering.